Hello friends, let us now study a very important aspects or process of food processing, that is micro encapsulation technology. This has a lot of potential for being used in different products for various purposes. So, this topic we will take up in two parts. In the part 1, we will study the basics of micro encapsulation technology, including different methods of micro encapsulation, and this will be followed by in the second part of the lecture on the application of this technology in food industry. So, first of all, let us understand what micro encapsulation is. In fact, micro encapsulation is a process by which very tiny droplets or particles of liquid or solid materials are surrounded or coated with a continuous film of polymeric material. The particles having diameter between 3 to 800 microns are known as microparticles or microcapsules or microspheres. You can see here in this picture that there is some active ingredient. This has been applied using a suitable process technology or process which we call micro encapsulation. A coating of the material is applied over it, and finally, we get a coated particle which we say that micro encapsulated particles. So, active ingredient is subjected to micro encapsulation process and we get micro encapsulated microcapsule or microspheres where these ingredients are protected. So, different processes why do we need encapsulation? That is the encapsulation, the answer is that it provides stability to the materials, it provides protection to the material, it might enhance acceptability, that is it might improve flavor and other properties of the product. It may even used for controlled release or targeted nutrition delivery or for immobilization purposes, etc. So, this encapsulation technology provides lot of benefits to the food processing industries as well as consumers, and this aspect particularly we will take up in the second part of the lecture. So, different terms related to the micro encapsulation technologies, as you have seen in the first slide, that there are some core materials, and on this core material some coating is applied, and this for application of the coating there should be some suspending liquid or vehicle through which this coating is applied, and finally a dehydration media, that is the solutions or vehicle which is used to apply this liquid is finally removed or evaporated from the material, so that the coating which is formed on the core material becomes rigid. It provides the structure or it provides the desired properties. Depending upon the different types of processes and materials used, the microcapsules of various shapes and sizes can be formed. Different shapes include simple sphere, multi-walled microcapsules, matrix particles, irregular shape microcapsules, or even multi-core microcapsules. The core material used in the micro encapsulation process might be a solid or it might be a liquid material. Coating materials generally used are polymers, waxes, resins, protein or polysaccharides. The vehicle to be used for microencapsulation may be an aqueous or even non-aqueous material. That is, so both aqueous and non-aqueous vehicles can be used for this purpose. Different coating materials which are commonly used for microencapsulation processes include water soluble resins like gelatin, gum arabic, carboxymethyl cellulose, methyl cellulose, etc. Water insoluble resins are ethyl cellulose, polyethylene, polymethyl cryolate, etc. Wax and lipids like paraffin, carnauba wax, bee wax, stearic acid, etc. can also be used as a coating material, or even different proteins like skim milk protein isolates, soya protein isolates, pea proteins, etc. are used for this purpose. So, there are certain points to be considered while deciding the core material as well as coating or wall materials. For example, the solid core materials can be mixture of active constituents, it can be mixture of stabilizers, diluents, expecient and release rate retardants or accelerators, etc. So, the core material either alone or in combination with various function improving constituents like stabilizer, diluent, etc. can be used, and they of course depending upon the type of the core material, type of the process to be used for encapsulation, they have to be properly, their quantity should be properly selected in proper proportion and proper type. As far as the coating and wall materials are concerned, they should be compatible and non-reactive with the core material. They should provide desired coating properties like strength, flexibility, impermeability, optical properties, non-hygroscopicity, tastelessness as well as stability to the materials, and more importantly they should be economic food grade substances. So, different techniques. Now, let us see what are the different methods which can be used for microencapsulation process. So, the techniques which are available for this purpose can be broadly classified into three major categories, that is physical processes, physicochemical processes and purely chemical processes. The physical methods of microencapsulations include pan coating, air suspension, extrusion, spray drying, freeze drying, microwave drying, vibrational nozzle and so on. The physicochemical processes include inotropic gelation, conservation or supercritical carbon dioxide assisted microencapsulation. The purely chemical methods include solvent evaporation and polymerization. So, in the next slide let us study briefly about the principle of operation of these methods individually one by one. And to start with, first of all let us see the pan coating method, and it is one of the oldest industrial procedure for forming small coated particles or tablets. As you can see here in this picture, the solid particles greater than normally 600 microns are considered essential for effective coating. The particles are tumbled in a pan or other device while the coating material is applied. The particles are taken here in the tumble and they rotate, that is it is rotating. So, obviously, the particles, the core material which are to be coated, it also rotates, and in this the coating material is sprayed using some atomizer nozzles. The coating materials are sprayed on the solid coat materials, and also usually warm air is passed over the coated materials, the process inside the pan, and while the material is being coated, and this warm air which is being supplied is actually helps in evaporating the solvent or the liquid vehicle, and it also helps in the formation of rigid layer or coating, or to it helps in becoming the coating looking thick or to provide its strength. The next process is air suspension or roaster process. In this method, the fine core materials are suspended in a vertical current of air and sprayed with coating material. After evaporation of solvent, a layer of encapsulating material is deposited on the core, and it gives improved control and flexibility as compared to the pan coating. Although the process is almost similar, but here the coating properties or coated material strength etc., is generally better than those obtained in the pan coating. However, this process has one major disadvantage, that is the agglomeration of the particles to some larger size is normally achieved if the process is not properly controlled. Then next comes the micro encapsulation using extrusion process, and there are three variations in this case. One is the melt injection, the other is the melt extrusion or centrifugal extrusion. In the melt injection, as you can see in this first figure, the core material is dispensed, or it is the core material which is dispensed in molten carbohydrate is pressed through one or more dyes into a bath of cold dehydrating liquid. The wall material solidifies, forming an encapsulating matrix to entrap the core material. The granules are recovered by filtration or centrifugation, and the residual solvent is removed by air drying or vacuum drying. The melt extrusion method is similar to that of the melt injection method. The major difference is that the melt extrusion method is a vertical screwless process, which you can see here in the second picture, whereas the melt injection is a horizontal screw process. In the melt extrusion process, this they contain surface washed particles, whereas in the melt injection process the particles are not surface washed. The third type of the extrusion technology for micro encapsulation include, that is centrifugal extrusion. It consists of a concentric feed tube through which, as you can see here in this figure, the bottom, that is the wall and core materials are pumped separately to the nozzle mounted on the outer surface of the device. Here there are different nozzles and they are pumped separately. The core material flows through the center tube and the wall material flows through the outer tube, and then it is dried and to provide that rigidity etc., that is either by air drying or vacuum drying. The process is used to provide rigidity to the microcapsules. Then next is the spray drying technology. which is the most commonly used encapsulation method in food industry. The process is economical and flexible. It produces particles of good quality, and you can see here in this figure the process involves 3 basic steps like preparation of a dispersion or emulsion which is to be processed. It is followed by homogenization of the dispersion and finally atomization of the mass into the drying chamber. Spray dried ingredients typically have a very small particle size, generally less than 100 micron or so, and which makes them highly soluble. So, this technology in fact spray drying method produces microcapsules of good solubility. Freeze drying is another good technology for micro encapsulation of the heat sensitive materials. It is also known as lyophilization or cryodesiccation. So, maybe essential oils or such the materials before drying, before freeze drying, they are first frozen, and depending upon the type of the material, the freezing temperature may range between -90 to -40 degrees Celsius, and after the material is frozen, then the surrounding pressure is reduced in the setup and enough heat is added to allow frozen water in the material to sublimate directly from the solid phase to the gas phase. And this freeze dried material seem to have the maximum retention of volatile compounds in comparison to those of the spray dried materials. Microwave drying is another technology for microencapsulation. It is based on a unique volumetric heating mode and internal vapor generation, which is facilitated by electromagnetic radiation of 2450 megahertz. We have detailed earlier studies about the microwave technology. So, it is the similar here also. Heating from the interior of a food product leads to the buildup of internal vapor pressure, and this drives the moisture out of the product, and a significant reduction in drying time is accompanied by an improvement in product quality. It is particularly beneficial or desired for encapsulation of the temperature sensitive products. The vibrational nozzle technology is based upon the railing instability. In this process, as you can see here in this figure, a fluid stream of liquid core and cell material is pumped through the concentric tubes and forms droplets under the influence of vibration. To guarantee production of uniform beads and to avoid large size distributions due to the coalescence effects during the flight, the droplets are passed through the electrostatic field, and as a result these droplets do not hit each other during the flight, and the separate individual droplets or microcapsules are formed. So, after having known about the physical methods, let us see now the physicochemical processes like inotropic gelation, which is also known as polyelectrolyte complexation, and this technique involves interaction of a cation or an anion with an ionic polymer to generate a highly cross linked structure. Generally, sodium alginate is used, which is first dissolved in water, and then in this solution of sodium alginate in water, polymers are added with continuous stirring. Also drugs are dispersed, and these polymers are dispersed drugs properly, they are placed on magnetic stirrer, and the ionic solution is added drop wise through needle, and which results into the inotropic gylations or microspheres are formed. The other technology is the conservation. Conservation is an unique type of electrostatically driven liquid-liquid phase separation resulting from association of oppositely charged macroions. The term conservate is sometimes used to refer to spherical aggregates of colloidal droplets which are held together by hydrophobic forces. There are normally two methods of conservation. One is the simple conservation and the other is the complex conservation. The mechanism of microencapsule formation in both of the processes is identical, except for the way in which the phase separation is carried out. In simple conservation, a dissolution agent is added for phase separation, whereas the complex conservation involves complexation between the two oppositely charged polymers. The general process consists of 3 steps which are conducted under continuous agitations, and the first step includes the formation of 3 immiscible chemical phase, maybe a liquid manufacturing vehicle phase, core material phase and the coating material phase. Then the second step is the deposition of coating, where the liquid polymer is deposited around the interface formed between the core material and the liquid vehicle phase. And finally, rigidization of the coating takes place, where the prepared microcapsules are stabilized by cross linking desolvation or thermal treatment. In this picture, you can see the process of simple conservation, that is the 3 stages: formation of 3 immiscible phase, deposition of coating and rigidization of the coating material. So, you can see here first that there are some droplets and these of core material they are put into a homogeneous polymer solution, and then it results into the phase separation process, where the conservate droplets of the polymer solutions are formed, all right, and this conservate droplets, they now get assembled on this core material, as you can see here, slowly and slowly, and finally this membrane formation takes place. So, formation of the 3 immiscible phases, then deposition of the coating second, and then finally membrane formation and rigidization of the coating takes place. So, in this way these microcapsules with the desired characteristic, desired strength are formed. The complex conservation process, here again you can see in this picture that in the first step, the emulsification of the oil in an aqueous solution containing 2 different polymers, generally polysaccharide and a protein. So, these 2 different materials are used. So, they are emulsified at a temperature and pH above the gelling point and isoelectric point of the protein. So, after the emulsion is formed, you can see here the IL and gelling solution is used and above 40 degree centigrade, this it is emulsion is formed. And then second step is the separation of the liquid phase from the insoluble polymer rich phase as a result of the electrostatic attraction between oppositely charged polymers caused by lowering the solution pH below the isoelectric point of protein. This finally, third step is the wall formation due to the deposition of the polymer rich phase around the hydrophobic droplets, followed by controlled cooling below the gelling temperature. And then wall hardening, that is the rigidization of the coated materials, results into the wall hardening of the microcapsules is achieved by the addition of cross linking agents. So, this is the complete complex conservation process. So, the other technology is the supercritical fluid technology, and in this you can see here in this setup, right. It is the similar to that are used for the supercritical carbon dioxide extraction of the biomaterials, etc. The same setup can be used with little modifications, and in the earlier classes we have studied in detail about the supercritical fluid extraction technology. So, in this setup, as you can see, it consists of a high pressure stainless steel impregnation vessel or impregnation unit. It has a temperature controlled bath, a magnetic steering plate, a pressure transducer and a high pressure carbon dioxide liquid pulp. So, in the process, this process can be conducted in the batch mode. So, the first impregnation cell is fed with a fixed amount of the core material which is to be coated. It may be essential oil or it may be some other material. So, it is put in the impregnation cell at the bottom, and then wall materials are placed inside a stainless mesh elevated from the bottom by a support, you can see here in the picture, and then after loading the oil and the wall material, the impregnation cell is immersed in the water bath at less than 80 degree Celsius temperature, and the carbon dioxide is then fed into the cell until the desired pressure is achieved, and once the desired pressure is achieved, the material is solubilized, that is it ensures the solubilization of the active ingredients in supercritical carbon dioxide, and then finally, the carbon dioxide finally the microcapsules are obtained. So, with this, now we come to the end of this lecture. In the first part, where we studied the basics of the microencapsulation technology, and we saw the methodology for the physical methods of microencapsulation as well as physicochemical methods. So, the second, that purely chemical methods of microencapsulation and its use in different food products or for microencapsulation of different food and bioactive ingredients by the industry. All these things we will study in details in the second part of this lecture. Thank you very much.